Yeah, thanks, Estella, for this amazing talk. And you made it easy for me to kind of do the transition to my second speaker. It's Peter Dueben. He is head of the Earth System Modeling section of the European Center for Medium Range Weather Forecast, ECMWF, developing one of the world leading global weather forecast models. It's the Integrated Forecasting System, IFS. He's also an honorary professor at the University of Cologne, and there's many things to tell about Peter, but I don't want to steal too much time from him, so please welcome Peter Dueben, telling us more about climate, weather, and so on. Thank you.
Thank you very much for having me. It's great to be here. It's my first supercomputing conference, so I'm kind of still amazed by the pure size of the whole thing here. I'm going to talk about, hopefully, the digital revolution of Earth system modeling. And Estella finished her talk with the video of a digital twin, so I just thought I should probably start my talk with a video of a digital twin. This basically, I just want to use this to kind of show you what Earth system modeling actually means, right? Basically, we have the Earth system. The Earth system is kind of, there are a lot of different components that are really important for the Earth system. There's atmosphere, there's ocean, there's the land surface, there are clouds, there's atmospheric chemistry, and so on and so forth. And we need to represent all of those in our models to kind of be useful. And this basically means that our models are very complex. So we're talking about 1 million lines of code or something like this. We also have a turbulent system, which is not very nice for computing in principle. So we also have the problem, obviously, that small-scale structures will kind of grow exponentially, and therefore we will also kind of lose predictability at some point. So it's kind of quite a tricky system to simulate in principle. However, the good news is that we're actually doing well, and we're kind of doing better and better and better over the years. So this plot here shows you the forecast accuracy of our weather prediction models. On the x-axis, you see time in several decades, and the y-axis is basically the forecast accuracy going up. And the different colors show you the different lead times that we have in predictions. So it starts with 3, 5, 7, and 10-day forecast from the top to the bottom. And what you see is it's getting better. So our models improve over time. There are several reasons for this. One of them is that we basically kind of increase our complexity, so we represent more processes. The other one is that we have more observations, so we're kind of getting better in really understanding what's happening right now. We're also getting better in what we call data simulation to bring the models and observations together. But we also kind of really have more compute power, and we can therefore increase our resolution of the models. And this kind of constant increase in quality was basically getting to known as the so-called quiet revolution of numerical weather predictions that kind of was there for us for several decades, but I think it's kind of fair to argue that this quiet revolution is coming to an end right now. So what's the reason? This is the reason. So that's the different supercomputers that we used at ECMWF over time. Again, x-axis is time in several decades. You see that the boxes are getting linearly increasing in size, which is basically an exponential law in a logarithmic plots, and that's Moore's law, as you all know. And so far, we could always kind of trust it. However, I'm getting a bit concerned about what's coming next, right? I don't think really we will see this kind of the compute power going up and up for the next years to come, basically. And that's unfortunate because this increase in compute power allowed us to also kind of go up with the red line. And the red line is showing you the resolution of the models that we're working with. So we now end up with something like 9 kilometers for our systems. And that's nice. I mean, that's basically already a high-resolution weather forecast, and it gives you really good results for a lot of things. But it's not sufficient, actually, to kind of involve important processes like deep convection in the tropics, like large thunderstorms, for example, and also the interactions with the topography. So I would really like that this number is going down further, and in particular into what we call the kilometer-scale range, where we really have just a couple of kilometer resolution. And as we don't really think that the compute power and the performance of the hardware will kind of really grow exponentially, what we have to look into is obviously the sustained performance, and to kind of make sure that we actually kind of get the most out of our ships. And this is what we kind of recognized in 2015 when we published this paper, and that paper is called the digital revolution. So the idea here is that you kind of really make sure that our models that are very complex and very difficult to actually kind of use efficiency on hardware to make sure that these models are actually kind of ready for the future. And for us, this means that we want to kind of make them kind of portable to different hardware architectures. So we need to think about domain-specific languages. We need to think about machine learning, how we can use it. We also need to think about like program environments and how we work with this. And obviously also the algorithms and kind of the way how we kind of scale these models to like a lot of different cores. And the good news there again is that also the digital revolution was kind of a success. And one reason why this success was happening was also via big projects like Destination Earth. So Destination Earth, as Stella already talked about it, has the ambition to build a digital twin of the Earth. So what you can see here is on the left side you have the simulation, and on the right side you have the observation. And even domain scientists typically can't tell you which one is which normally if you don't label it. So we are at a stage where we kind of really get a model system that is so close to reality that it's difficult to distinguish it from observations. And that should allow us both for weather and climate to really kind of make good experiments and have a good digital laboratory as well to kind of make, well, studies like what would happen, for example, if you would get rid of the rainforest in the tropics or something like this, and what would happen to the Earth system, what happens with climate change, and so on and so forth. And one of the core components of Destination Earth is the so-called Destination Earth digital twin engine. And the idea here is that you really kind of push those kilometer-scale models to highly efficient kind of methods and run them on scale at the supercomputers. And this also worked out fairly nicely in a sense that we can run these models now. I'll give you a couple examples for simulations that we performed on LUMI and LUMI-C and Mare Nostrum. And you basically see that we can run on a reasonable amount of nodes. We can run those simulations now at more than 100 simulated days per day. And this is kind of like a good quantity actually for us to have, because this means that we can now run these models on a reasonable amount of compute nodes kind of 2 decades into the future, and also kind of perform like operational weather forecasts in principle with these kind of amount of throughputs. And we can obviously also scale to kind of higher nodes and get bigger throughput, but really the good thing is that really happened in the last years is now that these simulations become really available for kind of research on a reasonable scale. And this is recognized by the community, so we just yesterday received 2 prizes from HPC Wire for our climate twin that is led by CSC, so you see Pirka here. And I think we are really up to something in a sense that we will see very great results in the next coming years about this. So Destination Earth and other projects basically made it possible to run those kilometer scales now and to really kind of look into the details. And the models hold what they promised in a sense that we really see kind of improvements on the local scale. For example, the sea ice cracks that you see on the top left. On the global scale in the sense that you also see interactions, nice interactions between small-scale features and large-scale features. And also in terms of the coupling. So on the right, you see kind of wind gusts and how they interact with topography. So that's a nice story. I'm now going to kind of switch the story slightly. What I have to tell you now is basically that the simulation on the left is producing better weather forecasts in terms of scores and root mean square errors than the simulation on the right. So on the left, we basically have a kilometer-scale model simulation with our physical model, the integrated forecast system. It's one of those kind of Destination Earth configuration. And on the right one, we have our machine learning model, the artificial intelligence forecast system. The left one has a resolution of 4.5 kilometers, the right one of 25. The left one has a time step of a couple of minutes, the right one of, I think, 6 hours. But the forecast scores in terms of forecast quality of temperature predictions, for example, is actually better on the right side. So the rest of the talk, I'm going to talk about the impact of machine learning that machine learning has on our domain right now, and it's kind of quite significant, really. This is a figure that is looking quite boring, I admit, but it's actually kind of quite scary when you're kind of in my position, because that's a figure that I copied from a paper from Google that they published at Christmas Eve in 2022. And what you see is the x-axis is time, and the y-axis are different physical fields that we have in our systems. And whenever you have a blue box, this basically means that the Google prediction with the machine learned model was better than the weather forecast prediction we have at ECMWF with our integrated forecast system for deterministic prediction. So basically the message from this plot is really, if you really just want to kind of have a good prediction of the future, and kind of you just want to know the temperature outside, for example, you should probably look into machine learning models. And there were a couple of companies looking into this, like Google, NVIDIA, Huawei, and they all built their own models basically to kind of run weather forecasts with pure machine learned models. These models don't know anything about physics, but they produce good results in principle. And we actually really had to kind of understand ourselves like what these models actually kind of mean, what do they actually predict and how do they work. And that's interesting in particular also because these models are actually quite special in the sense that they are not really a physical model that is kind of staying constant in time, like physically meaningful or something like this, but they're actually kind of showing interesting behavior. They're, for example, smearing out over forecast lead times. So what you have here, on the left, you see the truth. That's our era 5 reanalysis data developing in time, so that's what you want to predict. And on the right, you see one of those machine learning models that is kind of predicting in time, and you see that it's smearing out the structures as you go to kind of go from the top to the bottom and to further lead times in the future. So we were actually asking the question, like, how useful are these models then if they're smearing out and kind of showing like some sort of strange behavior in principle? So last year, we actually kind of really looked into this, and we tried to answer the most important questions for us in a way of like, how these model systems actually would kind of act and also how reliable the predictions are. So what we've done is, we first of all tried to kind of, or we kind of received the models from the big companies basically, and we're trying to run them in-house. And we're doing this successfully, so kind of to really look into the results on a daily basis for the daily weather forecasts. And we've done this over a couple of months, and in July, we were able to basically publish a paper about the results, and the results again show these models are actually useful. So it's not just the scores, it's also that they kind of are kind of fairly well predicting some of the extreme events, like for example, cold spells in principle, and they are kind of not really very unphysical in their behavior. So the next steps for us was to kind of publish those results as well. So if you go to our webpage, you will basically find weather predictions from a couple of those machine learned models into the future, and you can click really through the weather predictions, and this allowed us as well to engage with the community and to build trust to one extent, but also to get feedback for us in a sense of like how these models actually work and what they can and can't do. And then the next natural consequence was also that we built our own model. So we've kind of now revealed our the so-called AIFS model, which is our version of the machine learned model, and we are now also kind of competitive in terms of scores. So we really kind of are now playing in the same ballpark as kind of the existing models by the big companies. So how do these models work in principle? What they do is they take a so-called reanalysis data set. So that's a data set called ERA 5, and that's one that we also develop in-house at ECMWF. And here you basically take the observations and the model simulations of the past, and you generate the best possible picture of the atmosphere at a specific point in time over the last couple of decades. And once you have this, you can just train a machine learning model without any physical knowledge and just kind of update from one state to the next. And once you've learned the update, you basically are able to make a weather prediction. So that's kind of quite simple in principle. And also the models are not too complicated if you compare it. Like if you take a physical-based system model that's huge and complex, these machine learning models have basically fairly simple structures in principle. So you have some inputs that are kind of coming from different time slices. Then you have an encoder and decoder network of some sort. And then you have an output. And there are a lot of different network architectures actually also able to do this job for you. Obviously, some are better and some are worse. But in principle, it's kind of not that difficult. However, the models are obviously providing good results. So now going to go through a couple of the questions that kept us busy last year. One of them is also, are these models actually always smearing out if you kind of perform longer predictions? So how unphysical do they actually get? And also, can these models represent uncertainties? So these kind of just the forecast scores that I showed you so far were just for what we call deterministic predictions. So that's kind of the most likely temperature that you will see, for example, if you kind of will be in Atlanta in 5 days from now. But it's really also important to get uncertainty ranges. And here we normally perform ensemble simulations. And again, there was a Google paper coming out on Christmas, this time 2023, where they showed that you could use diffusion methods basically to generate those ensembles for machine learning models. So that's kind of not really surprising too much if you kind of know a lot about machine learning in that sense that you can kind of recreate small-scale structures and these kind of things. But it was kind of still good to see that you can run basically these models and also provide like good, like consistent trajectories that don't smear out, and also to have like a good results as well for like ensemble scores in principle. So Google was the first again, but we also did our job, and we kind of are also able now to kind of run basically ensemble simulations with AIFS and get good results, and there's a paper to come out in probably a couple of weeks from now. So the answer is yes to those two questions. The next set of questions was basically, how do these models perform for extreme events? So we have a model now that is trained from a couple of decades of weather data, but we want to predict events that are only happening every 100 years or maybe even 200 years. So how do the machine learning models actually behave for those events? No one could tell you. We have to look into the things. And also the physical consistency, like you train those models for mean loss functions basically, but does it actually not mean that you're getting kind of good results all the time, or does it mean that you get good results most of the time, but you actually miss the one important event that you kind of really care about? So what we've done is we looked into those forecasts for now 1.5 years, and we kind of constantly kind of evaluating the quality every week on a weekly basis against a physics-based model. And what we see again is the machine learning model is actually performing well, in a sense that there is not the one case where the machine learning model really didn't get it, but the physical model did. And on the contrary, there are some events, for example, this is an error pattern that happened, for example, for prediction over the US, where there was an interaction between the jet stream and the topography, and therefore kind of the physical models had some problems with it. So you see large patterns basically for the control forecast, which is our normal forecast for the ensemble mean, for the destination Earth prediction, the high resolution model. But the AIFS model on the bottom right actually performed fairly well in the sense that the forecast error was kind of limited there. So again, the answer to this question is basically, yes, they're performing well, and also for extreme events. Not for all events. Some of the events you kind of are still better with physics-based models, but for most of them, actually, you get a decent quality. Next question for us, can machine learning do data simulation? So far, the machine learning models were just taking reanalysis data. And for reanalysis data, you actually need a physical model to generate the data in the first place, because you need to kind of bring the observations and the physical model together to generate this kind of data set. So an important question is, can the machine learning models actually do this step for you? And so just for clarification, basically you're getting observations in, then you do the data simulation process where you bring the model and the observations together, and then you have a forecast model that you start, and you have post-processing for specific tools, and then the end user will get a product, for example, on their mobile phone. So why should machine learning be able to do data simulation? So first of all, why should it not be able to do data simulation? First of all, it is kind of much more difficult to actually kind of get good training data. So there's no such thing as a reanalysis data for observations. So it's actually kind of quite hard to kind of collect the data that you need in the first place and to bring it together. It's also that as you kind of go back in time for your data simulation process, it's actually getting harder and harder because you have less observations. And if you have less observations, you need to fill in more space, more like physical space where you have a gap of information. So you have a huge null space to some extent. So you see that we have observations on the order of 10 to the power of 8 data points, and you have a numerical model that is running at the order of 10 to the power of 10 data points. So you really have to fill in a lot of information. And also a question like what happens if, for example, satellites would just disappear or appear. So if you have a satellite that has a lifetime of 3 or 4 years and you need 1 year of training data to actually get it going into a data simulation scheme, that's not very useful. So it's kind of a lot of questions. On the other hand, why would it work? We already know that we can basically perform all the individual steps of a data simulation process with machine learning, so observation operators or kind of minimization or backpropagation through 40-var algorithms whatsoever. We can do all of this with a machine learning model in principle. And also we know that from the ensemble experience and also from downscaling experience that we can kind of generate small-scale features, so we can actually kind of fill in gaps that we have in the data sets. And also machine learning is just amazing, right? We have seen this in the forecast model. It can do things that we wouldn't expect. So why not here? There are a couple of studies that are out by now. One of them is Aardvark, for example, from Cambridge University. One of them is DiffDA that Thorsten Höfler has shown in one of his talks earlier, where that basically people already show that this is kind of in principle working. We have our own approach, and what we do is basically a bit ambitious, maybe too ambitious, I don't know, but the idea is that you actually don't do data simulation anymore. So you just don't bring observations and the model together, you just get rid of the model. So the idea is that you kind of take in observations on the left, and then you have a machine learning pipeline, and you spit out observation on the right, and the observations that you need, for example, the temperature on the ground. And by doing this, you basically get rid of the whole model state in principle. And results are getting there, in a sense. So this is a forecast error plot that I've shown you before with all the different lines for the different models. And the red dots are now our forecast errors that we get if we do the data assimilation with the machine learning. They're still higher than the lines, so still worse. But these dots are quickly going down over time. So I think I'm very confident that if I would give the same talk in a year from now, I would probably be able to kind of say, like, OK, data assimilation is done. So my conclusion is it's almost. So we're kind of almost there that we can also do data assimilation with machine learning. Next thing, physical understanding and predictability, like really to understand, to use the machine learning tool as a science tool is also interesting. So in general, the assumption for numerical weather predictions is that you kind of have small-scale features in your initial conditions that are incorrect, and then you run the model, and the errors are growing over time exponentially. And at some point, the scales of the errors are so big that they basically kind of destroy your predictability. There's a problem with this. So the good thing is if you increase your resolution, you will kind of gain predictability. The problem is the smaller and smaller the scales get, actually, the time scales will also get shorter and shorter. So that means that if you kind of increase your resolution by a factor of 2 and 2 and 2, you will only kind of gain less time in actually kind of forecast accuracy back. So this also means that there's a limit of predictability, and this kind of limit was postulated by Edward Lawrence and others a long time ago, and it's kind of known to probably all of you as a butterfly effect. However, in machine learning models, we actually see that we kind of can optimize initial conditions once we have the result of a forecast seen in real nature. So what we can do is we can basically take today's weather, and we can backpropagate the information and optimize initial conditions for 10 days ago, and then we will get the optimal initial conditions for the specific forecast. And we do this basically via the same mechanism that you optimize the neural network in a backpropagation way, basically. This has been done before within our conventional models already, but it's now much, much easier because it's more efficient, and also the models are easier to differentiate, actually, than the complex system models. And there's a team by Vonich and Hakim who basically showed that you can now make predictions of 23 days lead time, having those optimized initial conditions. That's kind of unseen for a lot of the fields. And the important part that they also show is that they don't need to improve the small scales of the initial conditions. So they can just improve the initial conditions on the large scale and get good results. This is definitely leaving me puzzled in a sense, like, what does it mean then for the butterfly effect? So do we actually need butterflies to do a good weather forecast? I don't know. So they're kind of interesting studies as well to be looked into. Another example is also coming from the Canadian Met Service. Normally, the assumption, again, for physical models is that they get the large-scale behavior right, and the small-scale behavior is difficult. The simple reason is the large scales are resolved properly. We know the equations, so we should be fine. And the small scales, we have problems with the subgrid scale features, but also we kind of are suffering, obviously, from impact of the subgrid scale on the solution. So this also means that the higher the resolution should be, the better the prediction in principle. However, on the other hand, we know that machine learning models are providing very good predictions in terms of the scores, but they don't really represent the small scales very well, and are really not really competitive, in particular because they lose basically this kind of small scale features over time, so the spectra is actually changing over time as you kind of go, as you run your forecast. So the Canadians thought about this and said, okay, let's just get the best of both worlds. So what we do is we take a physical model, and we now nudge the physical model to the machine learned model, because we know the machine learned model is doing well for the large scales, but we don't want to touch the small scales of the machine learned model. And they get very good results in the sense that they can really now run a physical model and get the benefit from the machine learned model in terms of the large scale scores, but they also get the benefit from the physical model when they, for example, look into very high resolution representation of the tropical cyclone, for example, and these kind of things. That's kind of something that is also very interesting, and we should definitely follow this up. And we also done this in-house now, and it's kind of also really getting kind of quite good results. So this kind of hybrid modeling where we also kind of combine machine learned model and physics-based model in the optimal way is also very interesting to look into. Another question, what about climate simulations? So we talked about weather a lot now because it's easier. You can verify what you're doing. But let's also talk about climate simulations with machine learning. Why would this not work? Well, first of all, you have to extrapolate. So what's happening is if you have a data set that is kind of looking into the climate of the last 40 years, for example, and then now you want to predict into the next 100 years, and you have anthropogenic climate change ahead of you, this means that the data distributions will change in time. So basically, you will have situations that you have never seen before, and we all know that this is always very problematic for machine learning in principle. The next question is how to represent CO2. So these models that I showed you so far, they don't even know CO2. They just realize probably that it's getting warmer over time, but we didn't really give them any information about CO2 in principle, and even if you do so, you will also need to extrapolate into the future. We also need more components. So for weather prediction, an atmosphere model is doing fairly well, but for climate simulation, you really need an ocean model, you need a sea ice model, you need aerosols, and all these kind of things. And you will never be able to represent the deep ocean, for example, correctly, because the deep ocean has like timescales of decades. You only have like 40 years of data or something like this, so how would you do this, right? I mean, you basically will fail to do this anyway. And also there's a question of trust, which is obviously very important for climate simulations as well. So you will never know whether your prediction is right in 100 years from now. With a physical model, at least, you have a better feeling about that. But this is kind of definitely also like a problem of will we ever be able to kind of trust those techniques. Why would it work? We can already do what we call AMIP simulations with our models. So we can run a model for like 20 years into the future, and we kind of get good results now with kind of the generative models and so on. So why not just run it for 100 years? And there are models that can already do this, like the ACE model, for example. So it's getting there. We can also learn all the components. There's no fundamental problem with this, and we're actually going to do this with Destination Earth as well, that we kind of build now an Earth system model in a sense that we kind of also build a machine learning model for the different components and put them there. There's no one really able to represent the deep ocean correctly in a sense that kind of we can be happy with it. In a sense, it's a really difficult task anyway, also for a physics-based model, and we have hardly any observations to control them, so it's kind of like already difficult enough for the physics model. We know, and I've already told you, that the machine learning models are very robust regarding kind of extreme events and so on, so why shouldn't they not work there? And also, I think that's probably the most important point for me, there will be machine learned climate model, there's no question, someone will build them. And if we have them, they're going to be basically better in a lot of diagnostics that we're kind of talking about right now than the physics-based model. So while I'm 100% sure that the climate modelers will not like the idea to have a machine learning model in climate, there will be these models around, and we'll have to see kind of what these models can and can't do. And one very interesting study in that regard was done by Thomas Rackhoff and others. So they were basically taking the machine learned weather forecast models now, and they were running them in different climate states. So the machine learned models have seen the climate state of 2023, but they haven't seen the climate state of 2040, 49, or 1955. So they're basically running out of their comfort zone. And they took a number of different machine learning models and were running them on a daily basis. And what you see in the plot is basically these kind of small hairs coming down. These are basically individual model simulations that they kind of spawn from this kind of climate simulation state. So there's one clear picture here, which is that the small lines all have a trend. So in particular for the future climate, you will see that the models are going down, which basically means that they don't like the climate they apply to. They're going back to their trajectory. They're basically kind of pushing the model fields back to what they're used to. So to some extent, these models failed. They didn't really embrace the new climate. They just kind of they wanted to get into the states that they know. So it's kind of a failure, if you want, in terms of climate modeling. On the other hand, actually, these models were useful already kind of for forecasts. Like if you look into the forecast errors that these models have in the different climate states, the forecast errors are actually kind of very small. And that means that they kind of can already provide some useful information for those climate simulations. So for example, for uncertainty quantification, to kind of check how extreme events will look like in the future, kind of based on one single climate trajectory and so on and so forth. So it's really kind of important that you ask the right questions, and then you will be able to do something useful with the machine learned model. But on the other hand, you obviously have to be very careful, and there are definitely things that the models cannot do right out of the box. So how will the physics-based and the machine-learned models now develop in the future? It's kind of a difficult slide, so don't remember me again in 10 years from now, what I've written down here. But I mean, I think it's clear that at the moment, machine learned models are really increasing in efforts, and this basically means, on the other hand, that the efforts for the conventional physics-based models will probably go down to some extent. And it's also clear that physics-based models will be replaced by machine learning models in many application areas. So if you have your mobile phones in 5 years from now, and you get it out and check for the weather forecast, I'm pretty sure this weather forecast will come from a machine learned model, because the score-based weather predictions are kind of better in a sense for machine learning models than for physics-based models. On the other hand, there's still a very strong need for those kind of physics-based models in principle. For example, for grace 1 weather events, something that you have never seen before. We know that machine learning models are somehow struggling with those, or can struggle with those. For tipping points in climate models, machine learning models will not be able to do anything there, I'm pretty sure. And also for the training of data generation, for example, if you really want to kind of have high-resolution training data, you need a physics-based model. The observations will not get you too far if you're really kind of up to the small detail and your postcode level weather prediction, for example. So we will still have machine learned model, physics-based models. But the development will change probably in a sense that we will go away from forecast scores and weather, for example, but really more to physical reasoning and physical representation, for example. And then also, I think we really kind of have to shoot for the best possible model that we can have, rather than just a model that is running every day, for example. And this kind of is also like another reason why we need to go towards the kilometer scale, and why projects like Destination Earth, for example, are useful. And then the models will need to be very easy to use, portable, and efficient, because it's already difficult right now to actually kind of find good people working on those models. If I go out in 10 years and ask for like a PhD student whether they're interested in running a 1 million lines of Fortran code model, they would probably say no. So I think we really have to think about how to kind of make those models very efficient and easy to use, because otherwise it's going to be very difficult. Then machine learned models, efforts in development will increase in principle. There will be many different application areas for machine learned models. And it's kind of unclear until this stage, like how many models we will actually have. So will we have a couple of models that are very large and very diverse, or will we have a lot of different task-based models that are small and kind of usable for a specific application? Data sets and models will increase in size. So the video that I showed you with the coarse resolution machine learning model and the fine resolution physical model, I'm pretty sure the machine learning model will try to catch up, kind of to have nicer videos and to have higher resolution, to have higher kind of fidelity as well. And this means that you kind of need higher model and like larger data sets to train from. And the question again is like, what is the limit? So will these models actually benefit the same way as you kind of go to higher and higher resolution like the physical models did? Probably not, but you still want to have high resolution. So it's kind of like, it's very difficult to kind of now judge where we're going to end up. And for the modeling centers, what does it mean actually? So I think we really have to continue to revise our physics-based model and make those tools really usable, easy to port, and kind of also probably think about different languages. And we're doing this we're following the Swiss approach of GT4Pi, where we basically are developing our new dynamical core in this kind of Python framework and having good results with a domain-specific language as well. But I think we will really have to kind of make sure that the models are shrinking and kind of be more portable and more usable. We will also have to embrace machine learning, and this is a process that's happening right now. So I think 3 years ago, we had the single machine learning scientist at ECMWF. Now I think we have 40 or something like this. So it's kind of really a process that is happening right now, and we really have to kind of make sure that we're following this. We have to embrace federated computing as well and federated data. That's also going to hit us. I haven't talked about this a lot, but obviously, kind of with projects like Destination Earth, we're now able to really port our model to the different supercomputers. This wasn't the case. Like 5 years ago, we were happy when we kind of could run on one other machine other than our own local machine. And now we are able to kind of run on a lot of different machines, and that's a good thing. We also need to kind of invest in more good visualization, kind of to also discover data efficiencies and these kind of things. So that's also something to look into. And I think we also need to kind of talk about differences between like how we use compute centers in principle. So how do we do operations? We probably still need our own hardware to kind of do operational predictions, but then we will have very expensive tasks to be done, for example, large-scale machine learning training. We need another data generation at high resolution and these kind of things, and we have to think about like how to do this scalable at for example, machines of EuroHPC and others. And the good news is I think we're doing very well. I mean, in particular in Europe, with those projects, we actually kind of really are, well, ready for the challenge, if you want. We kind of are able to kind of surf on the machine learning wave rather than drowning in it. And there's going to I'm looking forward to an exciting future there. So the last thing I want to talk about is foundation models. So Stella also had it on her slide as the new thing. And the question is, to me, basically, how many machine learning models are we going to work with in the future? We have a lot of different application areas that we can think of in a lot of different ways. And the question is, can we basically unify this approach? Can we have like a big model that can do many of those application areas rather than have small models that do the different applications? I'm not the first to talk about foundation models in principle, so there are examples like AtmoRep and ClimateX, Aurora. There was also one Gordon Bell Prize submission here, an Orbit, a foundation model for weather and climate. But we are going to build in Europe a new project called the Weather Generator that I'm coordinating, where we also have the ambition to kind of really build a large-scale machine learned model as a foundation model. So what's the difference to normal models? So the difference is that you really have a very diverse task application, basically. So we take all sorts of different data sets, whether it's reanalysis data or simulated data or observations, and you basically grab the observations wherever the data is. So if there's a local observation, you can use it wherever kind of point in time and space it was taken from. And you can all use satellite data, you can do model data globally, locally, reanalysis data, all these kind of things. And then you basically produce a lot of different outputs in the same way, and you can use these outputs in many different application areas again. And the core development act here is basically that you have a model that takes in those data sets on the left, and you have the data available on different kind of areas in space and also different kind of points in time. And then you erase some of the data sets, and you basically learned how to kind of project from one data set to the next. And this will basically allow you in the end to kind of just take observations in and produce a reanalysis data set, so that's data simulation. Or you can just kind of use information from the first 6 hours of a window and then produce data in the last 6 hours of a window, that's a forecast, and so on and so forth. And that allows you really to kind of use it very versatile. There are a lot of challenges for this. So one of them is that we really have the ambition to kind of run a model that you can run globally with a 100-kilometer course resolution, for example, but also the same model locally with 100 meters. You also want to kind of bridge hours of prediction time to decades in climate simulation, which is also not very easy for these approaches. You have a lot of complexity that you need to kind of somehow fit into token and memories, and we have to kind of find the best way to do this. We really need the power of the largest supercomputers if we really want to kind of have all the data sets that I mentioned. And also, we still need to show this kind of approach of generalization, that it's actually working. I mean, we would assume that those models are kind of more robust as well than task-based models, but that's still to be seen, and if they are not, then probably the task-based models will be much better for specific applications. So Weather Generator has really the ambition to kind of now build a tool that can be trained from petascales of data. It's kind of also something that is very special for our community. We have these huge data sets, right? We have an exabyte of weather and climate data at home at our institute, and we really want to kind of tap into this kind of amount of data. And we also want to use the full capacity of supercomputers, and that in particular, for our case, it's really the EuroHPC machines. Okay, that's it. Almost. I just have a summary slide here. I'll leave it there for you, basically, with a summary of the 3 revolutions. But I think the point that I want to make is you may or may not like what machine learning is, for example, doing to the domain right now. But it's really helping us in the sense that we will get better predictions. So I think all these changes that we have right now that are kind of quite sudden and quite drastic will actually lead to better weather predictions, and they will also lead to kind of better understanding of climate change and these kind of things. Thank you. There's a question. Hi.
Thank you. Good morning, and thank you for an excellent presentation. Can you say something about what are the machine learned models learning? Specifically, are they running the computational fluid dynamics? Are they learning the phenomenology? Are they learning statistics? What is it that they're learning?
That is an impossible question to answer very correctly, I guess. I mean, that's really something that we looked into 2023. Like, we really try to understand what do these models do. I think they normally learn statistics, I would argue. However, they're doing that in a way that it's kind of still very physical. The outcome that you get is very physical. So it's not that you get something totally weird or anything like this or so. So in a sense, you can also argue that they have learned physics. I don't quite think so. I don't think they've learned differential equations, for example. But they have learned basically to be so good in physics that they can to be so good in statistics that they can do physics correctly. That would be my answer. I'm not sure whether that's convincing.
Are there experiments you can do to find out what they learned?
Yes, there are. There are also like nice papers. Some of the papers do, for example, like phenomenological studies. So they change some of the fields and then they look into the response of the models. The models actually get it kind of quite right in principle, so they're quite well there. There are other papers coming out that are basically, for example, getting rid of all the strongest tropical cyclones that we see in the training data and then see what this is happening, for how this is influencing the results, and then they get mixed results. So it's kind of a bit, yeah, so they pass a lot of those physical tests, the models, but not all of them.
Thank you very much.
Yes?
No, great talk, thank you. You talked about physics-based models, physical models, versus AI models as two distinct things. I was wondering if there is an avenue for a hybrid approach. You could, for example, drop in a 3D radiation scheme that is machine learning based into a physical model. Is it worth exploring that?
Absolutely, we're doing this. I think it's worth saying that the first approach for us to look into machine learning as a forecast center was actually kind of to look into like putting machine learning into small parts of the model and trying to kind of use them there, like for example radiation schemes and so on. And then we were just kind of swamped by this pure machine learning wave, but people showing that they can do so much better if they can basically kind of do the whole thing with machine learning. So at the moment we're kind of a bit set back with the physical, these kind of hybrid solutions. But I showed you the results of the Canadians with the nudging, for example. There are also other papers like neural GCM from Google where I was also involved, where you basically kind of learn the whole physics with machine learning model, and it's all very interesting. So we're definitely looking into hybrid modeling. It's kind of one of our main 3 pillars for machine learning studies, basically. But I can't tell you whether this is going to be the holy grail in the end or not. It's kind of still to be seen, I guess. Yes, please.
Oh, I think in one of your slides you had a line that machine learning climate models will be bias-free, and then the next slide you showed it sort of reverting back to the climate it was trained on. Can you talk about that?
Yeah, what I mean is basically those machine learning models will be there, and whatever we can measure right now, in a sense, like how many tropical cyclones you will have, for example, in a year, what's kind of the average temperature of the Earth is, for example, in free-running simulations, if you keep pre-industrial constants, these kind of things. Whatever you can measure right now, machine learning models will be able to do that because they will also be optimized for exactly those diagnostics. So if you take a favorite climate diagnostics from nowadays climate, I'm pretty sure machine learning models will be able to beat conventional models in the future with it. But this doesn't help us if you want to predict 100 years into the future, because then basically the whole thing is changing, and we kind of still don't really have the trust necessarily that the model is doing the right thing. Does it make sense? Okay. Any other questions? There's one over there.
Yes, I have one. Thank you. Thank you for your talk. Very interesting. These machine learning models, like the one from Google, are end-to-end, and they mix solvers and trainable parts. So they use JAX so they can do the solver and things and have it different, use the different automatic differentiation to the gradients. What do you think about this kind of approach, how they will shake the world of parallel programming or programming supercomputers? Because we have the traditional way, Fortran, C++, whatever. It's not differential. It's not usable in this kind of hybrid models. JAX is emerging. I mean, say it differently, do you see like JAX being the future of programming supercomputers or something else?
So, very interesting. So you're referring to the neural GCM study, where you basically take a die core and then you, like a physical component of a physics-based model, and then you kind of train through the die core with JAX to kind of optimize a physical parameterization scheme. That's an extremely interesting approach. I have to correct you, so we already have a differential model. So IFS is differential, but it needs to be differential because you're basically running 40 var minimization in data simulation through the differential model. So it's nothing fundamentally new. It's just that these models are so much easier to use. You can basically just click a switch and you have a differential model there. And this will also have a strong impact. I can't tell you exactly how. I don't think that's kind of the revolution in itself because you can already do this. But with those models, I mean, I mean, these studies like Hakim and et al., I mean, they show the pure potential, what you have at your fingertips if you have a fully differential model. And yes, to some extent, I think that's kind of one of the parts where I would also think that the physics-based models really need to get their act together, because they really also need to be usable in the same way, basically, in the future. And there I agree with you that tools like JAX or others, the auto-defensible models that we really don't use because they're not stable enough for our community, we will have to think about how to use them in the future. Yes, please.
So you talk about using machine learning model to predict the weather 100 years from now. And right now, the machine learning model is struggling with events that haven't happened before. So how do you plan to benchmark the 100-year prediction, if not going back to the physics model?
Yeah, I'm absolutely right. I don't have a good answer to you, in a sense. I showed you that these models cannot really do it right now. We have to think about how to do it. You can argue that a foundation model, for example, will probably be more generic and kind of be more reliable as well. We are really at the very beginning of what we can do with those models. But state of the art today, I have no answer for you. Maybe in 2 years from now.
Yeah, nice talk. Actually, these extreme precipitation events are like more than two standard deviation or 3 standard deviations occurring at few places.
Yeah.
So that whether machine learning models can try to predict these extreme events, even the temperatures or anything.
Yeah, I think the issue here is that you're right. I mean, the extreme events are basically standard deviations away from their mean. On the other hand, if you train a model on a global data set, you have some sort of events that are happening somewhere else that are kind of actually inside of this framework, right? It's exactly one of those questions where we really struggle to believe the model in the first place, to kind of that it's able to do something like this. On average, again, the model is performing very well, also for precipitation events, and it's kind of surprising to us. I don't think that this means that we should get rid of physical models because for exactly also those events. I mean, you want to have a kind of in your backhand also like a model that can really, that you can trust, like with all the different individual steps. I think the mic is out, but also my chair is kind of coming up.
So, thank you very much,
Thank you.
Peter. And I think you probably can catch him here the next 5-10 minutes and talk to him. So thank you very much. I hope it was an interesting session for you, and I certainly learned a lot. There's still more to come. The conference runs until noon tomorrow. One thing I want to highlight is this afternoon, 12:45, in this room, we will have the SC24 awards session. So you can learn who gets the Gordon Bell Award this year, who won the student cluster competition, who gets the best paper. So I hope I see you all back there here at 12:45. Enjoy the rest of the day, enjoy the conference. Thank you for coming. Have fun.